All right, so the problem of the day, we had electrophilic aromatic substitution, and then the second problem had to do with nucleophilic addition to a ketone. I can wait.
Sure.
All right, so let's get started with problem number 1, which is our electrophilic aromatic substitution. I'm not going to draw the whole mechanism. I just want to explain the regiochemistry for why it chooses that 2 position over the 3 position. And so what we can do is draw both intermediates, and I'm just going to draw a generic electrophile E. And we can show at least simple arrow pushing, and we can say it can attack from that 2 position. Thanks. Or it can attack at this 3 position. If it attacks at the 2 position, our carbocation is down below. We get it right there. If it attacks at the 3 position, the carbocation is closer to the oxygen. And we get a electrophile added in here. All right, so how can we explain which one's more stable? Resonance. It's my favorite thing I like to drive home. So let's draw possible resonance structures, and we can say, okay, let's move this electron pair down. Oop. And if we do this, we still have our electrophile, but now we've moved our carbocation. Are there any other resonance structures?
Yes.
Yeah, we can move the lone pair from the oxygen down too, right? And so now that oxygen will have a positive charge. So we've got 3 valid resonance structures where that carbocation is delocalized across 3 different atoms. For the bottom one, we can delocalize the negative or the lone pair on the oxygen. Giving the oxygen the positive charge. And our electrophile is down here. Are there any other resonance structures?
Yes. But it's not okay though.
It's not okay though. A lot of people say, well, can we move that lone or that pi bond up? No, because then we'd violate the octet rule on that oxygen. So we've run out of possible resonance structures for this bottom one. So if we look at the top one, it's more delocalized, it's more stable, which means that's going to be the lowest activation energy intermediate, and that will be favored. So if you are running into a situation where you're seeing an aromatic ring where it's no longer benzene, and you can't remember if it's an ortho-para director, just draw out all your intermediates and see which one has the most stable intermediate. So compare your rhenium ions for both of those. All right, for problem 2, I sent you guys an email saying that I wanted correct arrow pushing. We're actually going to go through this mechanism in class today. I just wanted to get you guys thinking about it beforehand, so I'm going to leave this blank for right now, and then we'll cover it during lecture. All right, so yesterday we finished up talking about nucleophilic addition to ketones and aldehydes, and we said that aldehydes are more reactive because they're less stable. That means they're better electrophiles. And then we went through the simple mechanisms where we just use generic Nu as our nucleophile. We went through both of those. We said the difference was with the basic mechanism, we have nucleophilic attack first, followed by proton transfers. And then with the acidic mechanism, you have your proton transfer first, followed by your nucleophilic attack. And we said that these reactions are considered to be in equilibrium. We've seen them before with one-way arrows, like with a Grignard reaction. And it's important to remember that if your nucleophile is also a good leaving group, that the equilibrium will oftentimes favor the starting material side. And if the nucleophile is a bad leaving group, like a carbon or a methyl group, the reaction is going to favor the product side. And then we also said that aldehydes tend to be more reactive since they're more electrophilic. And then when we ended, we talked about all the different potential nucleophiles that we used. Today what we're going to do is we're going to go through some of these columns, specifically oxygen and nitrogen nucleophiles. So let's get a new tab where we talk about oxygen nucleophiles. And the first one we'll discuss is hydrates. And the overall reaction for forming a hydrate is pretty straightforward. We've already seen the basic mechanism, so I'll show a generic ketone. And then I'll show this reacting with water. And this is in equilibrium with a geminal diol, or simply called a hydrate. The mechanism for this is similar to our mechanism that we've already seen. But before we jump into that, let's take some examples of hydrate formations. Let's say I have acetone and water. This will form a hydrate where water will add in twice. And I'm going to leave out my equilibrium arrows. Let's add those in later. And then we're going to compare this to another one. So I'll leave this box. And then I'll fill that in so you don't need to put in a question mark. And then let's compare this to aldehyde. What's this aldehyde called? Formaldehyde. All right, so let's compare the equilibrium arrows for these two. Okay, so out of these two reactions, which one's going to favor the product more? The aldehyde, the formaldehyde reaction, or the acetone reaction?
How do you know?
So this is an interesting question. What's more nucleophilic, water or water?
Water.
Water. All right, what's more electrophilic? Our acetone or our formaldehyde? Formaldehyde is much, much more reactive because we said aldehydes are more electrophilic, right? So in this case, is the formaldehyde reaction going to favor the formation of the products, or is it going to like being where it's at starting with? It's going to want to form products. So we can compare the equilibrium constants for these, and we can clearly say that this one should greatly favor formation of our hydrate. And interestingly, with the acetone, the trend is reversed. In fact, with the acetone, you stay as 99.9% acetone. For formaldehyde, you'll stay as 99.9% formaldehyde. So this, again, is an example of hydrate formation where the balance of the equilibrium depends not only on the strength of the nucleophile, but the reactivity of your electrophile. So now let's go through and do the mechanism for this. And in particular, let's do the base catalyzed mechanism. We'll go through and do the acid catalyzed mechanism next. All right, so let's say we have our generic aldehyde. In this case, we'll use formaldehyde. And then we've got hydroxide. We know that hydroxide can be a nucleophile, attack our electrophilic carbon, dump electrons up to that oxygen. And we end up going through a tetrahedral intermediate. So in this case, we're going from an sp2 hybridized carbon all the way up to an sp3 hybridized carbon that's tetrahedral. And in the next step, we have our proton transfer, where this can grab a proton off of water. And the key in this reaction is that you regenerate your catalyst. And you end up forming what's called a hydrate. In this case, do you think the reaction is going to favor the product side or the starting material side? Product side. So not only do we have a very strong electrophile, formaldehyde, but now we've got an even stronger nucleophile, hydroxide. So this is definitely going to favor the product side.
I know you told me in your office, but will you tell me again how you know it's going to favor the product side?
So it's a combination of things. You compare the strength of your nucleophile and whether or not it's a good leaving group.
Oh, yeah, okay.
And then the strength of your electrophile. So in this case, we've got a really, really strong electrophile for formaldehyde, and then a strong nucleophile, which is hydroxide. Hydroxide's also a pretty good leaving group, but it's not the greatest leaving group.
Okay.
So in this case, we're going to, for the most part, favor formation of the products. It's still in equilibrium. It's going to be 99.9% on the right, probably 0.01 on the left.
Why don't you fix the arrows?
Okay, so we can do that.
Oh, sorry, I didn't mean to, I just wondered why you did it. Sorry.
There we go.
Okay.
So we can be nitpicky here.
Yeah.
Yep.
Are these hydrates different than the ones we see in the lab? They're like mono-ditrihydrates?
Yes, they're different. If you ever see a dot H2O, that's a different hydrate. That's usually in reference to an inorganic hydrate. Organic hydrates are an actual covalent bond to a new water molecule. Okay, let's compare this to the acid-catalyzed mechanism. What was the first step in our acid-catalyzed mechanism that we saw before? Protonation. So we're switching the order a bit. So in this case, we've got maybe hydronium floating around. So our oxygen can grab onto this proton, kick off water. Now we've got a really great electrophile where we can even draw a resonance structure where the carbon has a true positive charge. So the carbon is more electrophilic than in the base catalyzed mechanism. And then in the next step, we'll have water attack in. So water will be our nucleophile, add into the electrophilic center there. Again, we go through a tetrahedral transition state. Or not transition state, I should say intermediate. Now that oxygen has a positive charge. And then if there's still water floating around, the water can act as a weak base. Grab this proton, and we end up with our final hydrate. Again, the key for these reactions is you regenerate your catalyst. And you form a hydrate. In this case, again, the reaction would likely favor the product side because we're dealing with a very strong electrophile and we're turning our formaldehyde into an even stronger electrophile by first protonating it. So we'll go through and do a couple of these mechanisms for practice, but one thing I want to do is make a note just to drive this point home. The position of the equilibrium depends on the stability or reactivity. You can think of those as being similar concepts. Of the nucleophile-electrophile combo. So in the case of the Grignard reaction, where we have a really strong nucleophile, it'll favor the products. If we have a really strong electrophile, it'll favor the products. But if we have a weak nucleophile and a weak electrophile, oftentimes it'll just stay mostly at the starting material side. So that's an important distinction there. All right, now let's get into the example where we saw the reaction between an electrophile and an alcohol. So let's do acetal formation. So the overall reaction for acetal formation, actually let me change this to just acetone. You can react this with an alcohol. Use an acid catalyst. And you get this new product, which is called an acetal. This is really similar to our problem of the day example, where we had a ketone, and I told you you were reacting it with acid and excess alcohol. Specifically, you need two equivalents of alcohol to get the actual product. I know a lot of you maybe stopped at one addition of an alcohol, and that's fine. I just wanted to get you guys starting to think about the process here. But before we jump into the mechanism, let's talk about what acids are typically used for this. You can either have this acid. Let's see if you guys remember what this is called. What's this?
Nitric acid.
Nitric? There's no nitrogen in there. Close. Sulfuric acid.
Oh, yeah, right.
Okay, so you can use sulfuric acid. The really nice thing with doing this reaction is you can literally put a drop in and the reaction will work. The other reagent that's commonly used looks very, very similar to a reagent that we've seen before. What's this functional group called? Tosyl. And then we're going to put on an acidic group on there. So what might it be called?
Tosylenol.
Tosylenol? No, tosylic acid. And oftentimes we abbreviate that as just TSOH. So we've seen tosyl chloride used as a protecting group. If you change that chlorine with an OH, it becomes tosylic acid, and it's actually a pretty strong organic acid. So these are both occasionally used for the acid catalyzed reaction. You need very, very little of them. You just need enough to do that initial protonation step because we regenerate our catalyst in each of these reactions. So now let's go through the mechanism. And what I'm going to do is go through the mechanism for our problem of the day example. So in our problem of the day example, we had a furan. And it was a ketone. And in the first step, we're going to react it with a strong acid. So I'll just call this HA. It'll protonate our ketone oxygen, kick off our conjugate base. Give that oxygen a positive charge. Now we've got alcohol floating around. And in the problem of the day, we had, was it methanol? Yeah, it was methanol. So I'll call it homie.
do. I said, I don't. I swear. I don't want them.
All right, so the homie attacks.
I don't want them.
All right, and then in the next step, we still have excess alcohol around, and alcohols, just like water, can be a weak base or a weak acid. So in this case, we can show this deprotonating. It's important to remember it's in equilibrium. It's not necessarily strongly going forward. Okay, and then we've got our methanol that's protonated now. And that's a strong acid, right? So what might it protonate? Would it be the oxygen and the furan, the ether oxygen, or the alcohol oxygen? Alcohol. So the next step will be this alcohol grabbing that proton, kicking electrons back onto that oxygen. Okay, and the water in this case doesn't get shoved or doesn't fall off on its own. It gets maliciously shoved off by the oxygen on the ether. And when you do this, you form a resonance stabilized carbocation. And this looks unstable because you've got oxygen with a positive charge, but we know that it can delocalize. And this carbon can share that positive charge. So essentially we've regenerated a very good nucleophile, right? And then water was our byproduct in this reaction. If we have more methanol around, this can actually add in once more. And this will add into our electrophilic site. I know these reactions are very, very steppy, but bear with me.
You don't have a choice.
Okay. And then what do you think our last step is? Deprotonation. This can come, grab a proton, kick electrons back down. And we end up with our final product, plus we regenerate our acid. So in this case, we can form our final product, which is our acetal.
Is there nothing else that you can do?
At this point, you can't have anything else add in because we're not going to have any good leaving groups. So as long as you've got enough alcohol around, you can try to drive acetal formation. Another interesting thing to think about is, let's go up and look. Whoops.
Okay.
Just let me scroll up here once you guys are done.
You're super hot.
Thank you. Oh, sorry, that wasn't a compliment. All right, so if we look at the byproduct of this reaction, one thing I forgot to include is water. If we want to drive this reaction towards the product side, we can take advantage of Le Chatelier's principle and do a couple of things. What's one of the things we can do? It's not quite temperature.
Concentration.
Concentration, right? So if we increase the concentration of our alcohol using Le Chatelier's principle, we can drive formation of the product. What's another part of Le Chatelier's principle we can take advantage of?
You can remove some of the product.
Yeah, remove the product or remove the water. So oftentimes in these reactions, there are tricks you can do in lab in order to pull water out of the reaction and trap it at the acetal. Even if the equilibrium favors the starting material, you can drive it to completion by removing water out of there. There's a bunch of types of glassware that are used for this. We're not going to see them in our lab experience, but they're pretty neat. There's one called a Dean Stark trap, where essentially you start heating up your reaction. Water is usually the most volatile. It's the lightest in there, and so that will get evaporated up into the head of your condenser and then get stuck in this little side pouch, and you can remove water that way. So commonly you can drive these reactions to completion by using Le Chatelier's principle in there. All right, now let's take this one step further.
Okay. I just wonder who, like, comes up with this stuff. Like, what makes someone want to do it? I don't know.
Okay, so now let's think about this reaction. We don't have two equivalents of acid, we just have a diol. So let's think about what would happen here. And specifically, I'm going to scroll up to our last mechanism. And if you look at this point right here, this compound has a specific name where that alcohol is still on there, but we've only added in one alcohol. This is called a hemiacetal. Hemi meaning half. So hemiacetals are where it's halfway done. So let's figure out what the hemiacetal would be for this reaction.
Wait, is it one word or is it hyphenated?
It's, I believe, 2 words. I'd have to double check though. So I'll give you guys a minute to draw what you think the hemiacetal would be for this. So the oxygen on the carbonyl is going to become the alcohol, right?
Yeah.
And then one of the alcohols is going to add in.
Oh, because I'll have a positive.
Exactly. Right? Because only one end of the alcohol is reacting if we're stopping at the hemiacetal.
I don't know.
Come on.
Here, can we get some arrows?
So let's stop for a second. I've got a, what is going on? Sorry, not with an Apple product. All right, so if you look at this one, we now have a new reactive alcohol group that can add in. Oh my goodness. This, and this can displace water. And so what this is called is our hemiacetal.
How did you? I'm really lost right now.
No, we'll go through and do the mechanism. There we go. It wasn't letting me scroll down for a bit. So when you've worked with diols, specifically diols with 2 carbons in them, you can get what's called an acetal that's a cyclic acetal or protected alcohol, or a protected acetal. Why might this be favored compared to having 2 diols attack in separately?
Cyclic systems, stable.
Oftentimes cyclic systems are stable. Another thing you can think about is disorder or entropy, right? Would you prefer to have more molecules come together? Is that entropically favorable?
No.
No. So in this case, by having one molecule close down on itself, it's actually entropically more favorable than having another molecule add in. So let's go through the mechanism for this one. This one's kind of crazy.
Hold on. I'm scared. It's super long.
It's long like the last one, but it's good practice. So first step is going to be our protonation. And what acid might we use here? Sulfuric. Why wouldn't we use something like hydrochloric acid? Because chlorine could be a good nucleophile, right? If we think about the conjugate base of tosylic acid, it's a terrible nucleophile. So in this case, we want to use an acid where the conjugate base is non-nucleophilic. Then we can have one end of the alcohol add in. That gives the oxygen a positive charge, right? What's the next step? We're not quite to our hemiacetal. Deprotonation, right? So in this case, I'm going to just shorthand our conjugate base, which is A minus. It could be another alcohol group. Really,
What's the purpose of a hemi?
the hemiacetal is just a halfway intermediate. Okay, so now we're at our hemiacetal. We've recreated our acid, right? So what do you think the next step will be? We can protonate our alcohol, right? In reality, the equilibrium would potentially favor both alcohols, but what might be a driving force for this alcohol getting protonated? It can get kicked off as a leaving group, right? Our other alcohol can't get kicked off as a leaving group because it doesn't have lone pairs nearby to kick it off. So we've got water as our leaving group, and it's in close proximity to the oxygen over here. So we can say, well, these lone pairs can go down and maliciously kick off the water. Well, the thing that a lot of people get confused on is they want to draw this as an SN1 type mechanism where the water falls off on its own, forming a carbocation. But in reality, it's the lone pair driving it off. Otherwise, we would protonate that other alcohol and have that leave. Okay, so we're almost ready to go. So now this oxygen can reach around and attack into the electrophile on itself.
Oh, that's what gets the ring.
Exactly.
Or the six or whatever.
And this is entropically more favorable than having another molecule come in and attack. And then the last step, we've got our conjugate base, which can come and act, or come deprotonate this last ether on here.
And we regenerate.
Yep, and then you regenerate your catalyst.
Why do you want to regenerate your catalyst? Do you care?
It's not even a matter of wanting to, it's just a matter of it happens, right?
But is it like better in some way?
Well, let's think about it. Would you prefer a reaction where you have to dump in a tanker car full of acid, or a couple drops? Couple drops. It's way more efficient to run this reaction, and you can get your cyclic acetal.
Which is more safe?
Okay, I remember when my undergraduate advisor showed me this, I thought he was just making me do difficult mechanisms because difficult mechanisms are fun for science teachers. But that's not the full story here. Cyclic acetals are actually very commonly used, because if you think about it, is this carbon electrophilic anymore? No. So we've taken a ketone, which was electrophilic, and we've turned it into a cyclic acetal that is no longer electrophilic. Why might that be useful?
Why it is non.
So we turned an electrophile into a non-electrophile.
I don't know, use it as a solvent or something.
This goes back to a couple terms ago. What do we do to a group when we don't want it to react? We protect it, right? So with alcohols, we protect alcohols when we don't want them to react. If we have a ketone we don't want to react, we can turn it into a cyclic acetal. That makes it something that's no longer electrophilic, and we can protect it.
Is this kind of like, this is probably so off topic, but is this kind of like that plant that like shrivels into itself to protect itself? Like how that just turns into a ring to protect its like.
It's not biology.
I'm not a biology teacher, I'm not sure. All right, so now let's talk about this.
Wait, did you make a comment saying you could not use hydrochloric acid on?
Yeah, hydrochloric acid, the chlorine that gets ejected off can be a weak nucleophile. Okay, so
So you might get some byproduct of it adding it instead.
in this case, the acid we used, the conjugate base, is non-nucleophilic.
But if we use the HCl, that's what I'm talking about.
What about it?
If we use HCl, when the chlorine gets kicked off, it could then add in possibly.
Mm-hmm, definitely.
Dr. Engel, I'm being serious. Do we have a party at the end of the quarter?
We will. All right, so it turns a ketone or an aldehyde, which is electrophilic, into a cyclic acetal, which is non-electrophilic. Which means it's a protecting group for ketones and aldehydes. Oh. Okay, so let's think about this and put it into an example. Let's say we've got this cyclohexanone, and next to it we've got an ester. And our goal is to do an organic transformation where we convert the ester into an alcohol. What reagents are normally used to convert an ester into an alcohol? We're reducing it.
Oh, you could use, was it LAH, I think?
Okay, so if we use lithium aluminum hydride, what's the problem we're going to run into?
Carboxylic acid. What is it? Carboxylic acid.
No, if you react an ester with LAH, you'll get your alcohol.
But on this, you get a diol.
But on this one, we've got a ketone that could also be reduced, right? So we need to come up with a system for making the ketone non-reactive, but reacting only the ester. So how can we maybe do that? Exactly.
Good job, Adrian.
So if we react it with our ethylene glycol, we use a catalytic amount of acid, and we drive off water from the reaction. We can protect that ketone. Why doesn't it do the same thing with the ester? Because it can't, but why can't it? We can accept it as faith. Maybe somebody wrote it on a tablet and it dropped from the sky. Or we can just say that ketones are more electrophilic than esters, right? So if we're going to do an acetal formation, it will only work on ketones and aldehydes. It won't work on carboxylic acids or esters. So in this case, we take the ketone, which is more electrophilic, and we can install a protecting group. And I'll just abbreviate that PG. All right, what do you guys think the next step in this synthesis should be?
Now we turn that ester into alcohol.
Yeah, now we can turn the ester into the alcohol because the ketone is protected. It's no longer electrophilic. And what reagent did we say we need? You can write it as LAH or lithium aluminum hydride if you want to. And in this case, we need to be sure to use excess. That way we kick off that methoxy group as a leaving group. So this goes back to our chapter on alcohols. All right, now the big question. How do we get rid of our protecting group? How can we force the equilibrium to go backwards in favor of starting material? Add water, right? Because we said in order to drive the reaction to the product side, we remove water, taking advantage of Le Chatelier's principle. If we want to do the reverse direction and actually favor the starting material side, we just add more water, right? So in this case, all you have to do in order to remove these protecting groups is add a catalytic amount of acid and add water, and you can get the reaction to go in the entirely reverse direction. So once you're done doing all of the other reactions on your molecule, you want to remove your protecting group and go back to your original ketone. And again, we're using all of the Le Chatelier principles that we learned back in general chemistry. Do you guys want to do another example problem? All right.
No, why are you out? Hey, I'm serious about the party at the recording.
We'll have a barbecue at the end of the quarter. I'm trying to organize it right now.
We deserve it.
All right.
Professor, you should call it a barbecue. I didn't say that, I gave you. You just didn't want to say
I didn't think it was funny to say forever.
Well, I'll pretend we have a
1, 2, 3, 4.
I told. It's the on
He is now.
Sorry, guys. 2, 4, 6, 7. 2, 4, 6. All right. We're not going to name this one, but
Why not?
Yeah, practice, he said.
Just do alcohol or ketones take priority.
this gets into conflicting priority rules. So let's avoid naming these for now. I'm going to give you guys. They do get really, really complicated. As soon as you've got conflicting priorities, then you get into this obscure list of rules and order of rules you have to follow, and I'm not going to push that on you guys. But let's take this example and try to figure out the product that we would get out of this.
Is there a class just on naming?
Not really. Yeah. There are computer programs that will spit them out for you.
Why can't we get the hookup?
All right, what's the first step?
We're gonna grab the oxygen's gonna grab the
Rotate
hydrogen.
the ketone?
Protonate the ketone, right?
Yeah.
So just like in the previous reaction, you can say,
Really. Just need to come out of it.
Okay. In this reaction, I didn't add any water. I didn't add any excess alcohols. I just put in a drop of acid. What do you think could maybe happen?
Maybe the alcohol too
Yeah, we've got an alcohol in our parent molecule, right?
wraps around.
So could this cyclize, do you think?
Yeah.
Yeah.
Okay, let's draw the cyclized product and see what that looks like. And when I do these, I always like to number them too, so I don't lose anything. 4, 5, 6.
Professor, are you trying to pull a fast one on us, or can I draw this without having to worry about erasing it?
No, I've got it. All right, so our 1 position has attacked the 6th position, and on the 6th position we have now a methyl group.
Alcohol. Alcohol.
And then we've got an alcohol. Oops, shoot. And then we also need to remember that this oxygen that got added in is now protonated. Shoot. I'm not being careful with erasing. Let me move these to the inside. Okay, what do you think the last step is going to be? Okay, so if we've got our conjugate base around, we can say, all right, maybe this can come deprotonate. All right, so now the question is this an acetal, a cyclic acetal, a hemiacetal? What sort of functional group would we call this final product?
Hemicyclic
I agree.
acetal
I agree.
or not?
Hemicyclic.
So did the alcohol have the capability of adding in twice?
No.
No, so it's not an acetal. In a cyclic acetal, you have 2 alcohols add in. We only had 1 alcohol add in, so it's not a cyclic acetal.
Hemi.
It's just a
I
hemiacetal.
thought when it, since it made that it would be cyclic.
So it is a cyclic hemiacetal. The interesting thing to think about is most of the time I told you guys you'll go to the acetal, but in this case you're kind of stuck at the hemiacetal. This may come into play with the problem of the day that I gave you guys, and this is highly favored because we're forming a 6-membered ring. This is very, very common in carbohydrate chemistry. So on your problem of the day, I'm giving you guys an intro into biochemistry and how carbohydrates behave. All right, I think we're going to leave it there, and then we'll cover nitrogen nucleophiles tomorrow. Okay, just 1 second.